So I'm Thad Szabo. I teach astronomy and physics at Cerritos College. If we look at the expansion of the universe, at first it was thought that as things are expanding, well, objects have mass, and the mass is going to be attracted to other mass, and that should slow the expansion. Then in the late 1990s, you have these supernova surveys that are looking deeper into space than we've ever looked before, measuring distances accurately to greater distances than we ever have before, and something really surprising came out, and that was what we now use dark energy to try to explain, and that is that the acceleration isn't slowing down, it's not even stopped, it's actually getting faster. And if you look at the most distant objects, they're moving away from us. The acceleration is increasing, the acceleration of expansion. And this was a hugely surprising result. Some of the ideas to try to explain it, one is the idea of a cosmological constant, which is something that Einstein had introduced into his field equations to try to keep the universe the same size. He didn't like the idea of a universe changing, and so he just kind of cooked up this term and threw it into the equations to say, all right, well, if it's supposed to expand or contract, if I make this little mathematical adjustment, it stays the same size. Hubble comes along about 10 years later and is now observing galaxies and measuring their redshifts and their distances and says, wait a minute, no, the universe is expanding. And actually, we should really credit that to Georges Lemaitre, who was able to interpret Hubble's data to come up with the idea of what we now call the Big Bang. All right, so the expansion's happening, wait, it's getting faster, and now the attempt is to try to understand how dark energy works. Right now, most of the evidence points to this idea that the expansion will continue in the space between galaxies, that the force of gravity, and especially the forces of electromagnetism and the strong nuclear force that holds protons and neutrons together in the center of an atom, would be strong enough that dark energy is never going to be able to pull those objects apart. However, there's a possibility that it doesn't work like that, and there's actually a little bit of experimental evidence right now. It's not well established, but there's a little bit of a bias with certain experiments showing that dark energy may get stronger over time. And if it does so, then eventually the distances won't matter, that any object will be pulled apart. So first, you will see all galaxies recede from each other as space starts to grow bigger and bigger, faster and faster. Then the galaxies will start to be pulled apart. Then the star systems, then planets from their stars, stars themselves, and then other objects that would typically be held together by these much stronger forces, the electromagnetic force. Objects held by that will be pulled apart. And then eventually nuclei and atoms. If dark energy behaves so that it gets stronger and stronger over time, it will eventually overcome everything, and you'll have a universe with nothing left. And that's the big rip. If dark energy gets stronger over time, it will eventually overcome any forces of attraction, and then everything's torn apart.
Thanks for watching. Now make sure you click subscribe on our YouTube channel here. And maybe you still got some questions about space and astronomy, like this one, or that one. And if you don't see what you're looking for, then send me an email at info@universetoday.com.
Not even a blooper reel?